Hello, everyone. I'm Norman Wahlberger. Thanks for joining me on this adventure. We are looking at dynamics on graphs. So today we're going to look at a very interesting new development. I want to introduce what's called the numbers game on a graph, but there's actually another game that comes before that, which I'll mention, called the pentagon game. So these are, in a quite very natural way, duals to the mutation game, and it's going to be really important for us to take these on board so that we have this sort of balanced view of the dynamics on a graph. Mutation game on one side, the numbers game on the other side. Okay, so the very interesting story here that really starts with an IMO problem. So IMO stands for the International Mathematics Olympiad, and in 1986, problem 3 of this international competition was submitted by Elias Weigert. And it's a very interesting challenge problem. It's actually probably one of the most difficult problems that's appeared on the International Mathematics Olympiad. And if you would like to know more about the story of how this problem sort of generated a lot of interesting things, I highly recommend the paper Relaxation Procedures on Graphs by E. Weigert and C. Rayer, which appeared here in Discrete Applied Maths in 2009. And it's available on Science Direct, so you can just download it directly. Okay, so here is the pentagon game. Okay, and I want you to think about this because this is going to be very relevant to our approach to dynamics on graphs. Okay, it's a very simple case, but it's still highly non-trivial. So 5 integers with positive sum are assigned to the vertices of a pentagon. If there is at least one negative number, the player may pick one of them, say y, add it to its neighbors, x and z, because we're in a pentagon, so any vertex has exactly 2 neighbors, and then reverse the sign of y. Okay, so that's what you do. You pick a negative number, you add that negative number to its direct neighbors, and then you reverse the sign of y, so it becomes positive. The game terminates when all the numbers are non-negative. Prove that this game must always terminate. So, a great exercise, challenging because International Mathematics Olympiad problems are challenging at best, and this is one of the harder ones. So it's well worth being modest about trying to solve it. But I think it's really great for you to think about it because it'll be a great introduction to this whole approach of the numbers game. So this game was then extended by Shahar Moses to become the numbers game, so quite a big generalization. And that was introduced in a paper in 1990 called Reflection Processes on Graphs and While Groups in the Journal of Combinatorial Theory, and here it is there. So we are very interested in these 2 games, well, the numbers game especially, but the historical aspect connecting with the pentagon game is interesting too. But we are going to look at the numbers game in a very different way. So I want to introduce this as essentially a dual game to the mutation game. So this will involve some new objects which are sort of dual to populations. So populations, are typically row vectors. These dual objects are going to be column vectors, and we'll call them weight vectors or just weights. So that has some resonance with people who know about Lie theory, and there's some connection with the terminology that appears in Lie theory. But this is, in fact, much more general than what's happening there because it works pretty well for any graph. Okay, so I want to illustrate the story, by looking at a specific example where I can illustrate things very concretely. So let's have a look at this favorite graph bars that we've seen a number of times. Let's label it now as with vertices 1, 2, 3 along the bottom and 4 up on top, all right? And then the adjacency matrix will be this one here, A. Okay, so the first column, you see the number 1 is connected with number 2. And in the second column, number 2, or vertex 2, is connected with 1, 3, and 4. And in the third column, vertex 3 is connected with 2 and 4. And in the fourth column, vertex 4 is connected with 2 and 3. So that's the adjacency matrix of a graph. Since we're talking about simple graphs here, this is necessarily just consisting of zeros and ones, and it's symmetric. Okay, so now population, remember, is just a function, integer valued function on the vertices. So that can be now identified with a row vector because we've we've organized these vertices. We basically ordered them. So 1, 2, 3, 4. So a population can then just be exhibited by the row vector, which just enumerates the values at 1, 2, 3, and 4. Say P1, P2, P3, P4. And let's just remind you that if you take this row vector and you multiply it by A, then, well, you're getting sort of at each vertex position, you're getting the sum of the neighbors. So at 1, you're getting P2, and at 2, you're getting P1 plus P3 plus P4, and so on. And each of the columns of A is responsible for one of these entries. So, for example, this P2 is really coming from this first column. That's how you multiply things, and this one here is coming from the second column, and so on. Okay, great. Now, corresponding to this graph, there are mutations. Okay, and these mutations, I remind you, act on populations. They change a population. So if you mutate a population at, say, at the vertex 2, then something's going to happen at 2. And let me remind you what happens, okay? That, first of all, the population at 2 negates, and sort of to combat that, each of the directly adjacent vertices, which in this case are 1, 3, and 4, will clone their populations and send those populations down these roads into the mutating city to sort of cancel perhaps the mutations that appear there. Okay, so we've seen that when we express populations with vectors like this, then these mutations can be expressed with matrices. So the matrices act on the right of these row vectors. Okay, so for example, S1 is given by this matrix. Let's just actually make some let's clear definitions. Okay, and I'm just going to make these definitions. So that's S1. So we have that. That's the mutation matrix for the mutation at the first vertex. Here's S2. Here's S3. And here's S4. Let's just check that we have them there. S1, S2, S3, S4. Okay, good. So for example, if we take P, this thing here, okay, P1, P2, P3, P4, a general population, and we act on it by S2, that is, we multiply this row vector by the matrix on the right, then we get P1, P1 minus P2 plus P3 plus P4, P3, P4. So we see that we're just getting effectively the mutation at vertex 2. It's negated the population at 2, and it's added a copy of the neighboring populations. And let me remind you how you get one of these mutation matrices. Okay, you can get it in a very simple and direct way. Basically, just if you have the adjacency matrix in front of you. So, for example, to get this S2, how do you get that? Well, you start with the identity matrix. In this case, the 4x4 identity matrix has 1s down the diagonal, and then you change the 1 in the ith diagonal position. I is 2 in this case, so in the second position, we change that 1 into a -1. Okay, and then you're also going to change the elements in that corresponding column through that diagonal entry by basically looking here to the adjacency matrix, picking out that second column, and basically adding that second column to what you have here. Okay, so there's various zeros that were there, and those zeros have been replaced with 1s. So let's just show you the same thing for S3, for example. You start with the identity matrix, you negate the third diagonal entry, so that becomes a -1, and then you look over here on the third column of the adjacency matrix, and you basically just add that to what we have over here. So you're adding the 1 here and the 1 here. Okay, so it's very simple, actually, how to get these mutation matrices, basically just fiddling around with the identity matrix and with the adjacency matrix. Okay, so now I want to introduce the weight vector W of a population. Okay, so I'm going to introduce this duality. So for every population, there is a corresponding column vector called a weight, or a weight vector. And I want to proceed with an example. So suppose that we consider a particular population P on this graph X up here. And let me just remind you, maybe I'll just copy that just so it's clear in your mind. Okay, there's our graph. All right. Okay, so we have a population 5, 4, 2, minus 1. So there's 5 at this vertex, there's 4 at this vertex, there's 2 at this vertex, there's minus 1 at this vertex 4. So let's copy that. So now the computer knows what P is. So I, how much? Well, it went from 5 to minus 1. So altogether the change is minus 6. Okay, what about if we go back to the population P and perform mutation S2? Well, we're getting 5, 2, 2, minus 1. So none of them change except for the second one. And that becomes a minus 4. And then we have to add minus 4, the sum of the neighbors, which is all of the above. That's 6. So minus 4 plus 6 is 2. That's where there's a 2 there. Okay, so what happened to this entry? Well, the second entry, when we perform the mutation S2, changes by, in this case, minus 2. Good. Okay, what happens if we happen to do S3 to the original thing? Well, we get 5, 4. It only changes here, so the 2 changes to a 1. So we can say that the third entry changes by, the 2 goes to a minus 1. And finally, if we do the fourth mutation, S4, then only the last entry changes. The minus 1 goes to a 7. And we can record that by saying the fourth entry changes by, we went from minus 1 to 7, so it's a change of 8. So suppose, for example, that your aim was to play the mutation game in such a way as to increase the population. That's a kind of a nice orientation to have, right? We start with the population. We're interested in increasing the population by judiciously making mutations. So this information that's down here in this little column here, it would be very convenient for you, because you would know that if you were faced with this particular population, that these numbers would be telling you how much you can expect the population to change by with respect to the successive mutations. In this particular case, all of the mutations decrease the population except for the last one. So if your aim was to increase the population, you know that you would have to do an S4 to this particular thing. Okay, so we record all this information, by a, well, we'll call it a weight vector, okay? So it records all the changes to the population P for all possible mutations. Okay, and we're going to make a vector. So let me take one of these, maybe. I'll take a transpose. Okay, there's a vector. There's a column vector. Okay, and what do I have to fill it with? The first one will be minus 6, the next one minus 2, the next one minus 1, and the next one 8. Okay, so there is then a correspondence. There is then a correspondence between the population P equals that, and maybe we'll give this a name, let's say W for weight, how's that? Between the population P and the corresponding weight, this thing, maybe I'll make a new line so we can see both of them hopefully on the same thing, right? So there is then a correspondence between the population P and the corresponding weight W. Here is the essential duality that's going to play a huge role, okay? So that now we have a kind of a balance situation. We have this population, but now we have a corresponding weight sort of associated to it. And now I'm going to, let's say I'm interested in playing this mutation game and increasing the population. So I've said that, okay, I should really multiply by the mutation S4 here to increase the thing. So we saw that, let's say Q equals P of S4. So if we apply the mutation S4 to P, we end up with this population. Let's call it Q, all right? Let's now calculate what the associated weight is for this Q. Okay, so this is a fun calculation. Let's find the corresponding weight for Q. Okay, so what am I going to do? Well, I'm going to first define Q. So over here, I will get rid of that and we'll just make a definition, Q. All right, and now I'm basically going to copy the same thing that I did over here. Three changes by how much? 5 goes to -1. That 5 goes to -1. That's a -6. That's the same thing it was before. Okay, what if we apply S2 to Q? Okay. What has happened to the second entry? So going from 5427 to 5127, we see that the 4 has gone up to 10. So the second entry changes by +6. Okay, good. What if we do the mutation S3? We get 5497. Then the third entry went from 2 to 9. All the others stay where they are, which is a change of 7. And finally, we do QS4. The fourth entry has gone from 7 to -1. The fourth entry changes from 7 to -1. That's -8. Okay, so now we record this information. We can just copy this thing here. Record this information by a weight vector. Record all the changes to the population Q now. Okay, and what is this weight vector? The first one is -6. That hasn't changed. Then the -2 is now a 6. The -1 here changed to a 7, and this one changed to a -8. Okay, so I'm going to copy this. So there's then a correspondence between the population Q, which was 5427, and the corresponding weight, which is this one here. Maybe we'll call it something else. W, say U, all right? Okay, so now I want you to observe the relationship between these two things here, okay? So we started with the population P, and here was its corresponding weight vector. And then we applied, what did we actually apply? We applied S4, right, to get from P, the population P, to the population Q. What happened to the S4? So that changed the fourth entry, okay? Now let's have a look at what happened to the corresponding weights. The corresponding weight went from W -6, -2, -1, 7 to -6, 6, 7, -8. What's the relationship? Can you see a relationship between this vector and this vector? What's actually happened? And I better remind you about our graph. We're actually looking at this graph. Okay, we're looking at the graph. Maybe I'll put it over here. And to go from P to Q, what we did is we mutated at S4, at the vertex 4. Okay, there's a mutation S4 linking this thing to this thing. Okay, so correspondingly, what is the relationship between this and this? Well, it probably has something to do with the fourth entry, increased by 8. The -2 has gone to 6. That's also increased by 8. And notice that 2 is also a neighbor of 4. But the -6 at 1 has not changed. So the effect is, well, here's one way of explaining how to go from here to here, okay? That what's happened is that we've taken this 8 at vertex 4 and added it to each of its neighbors, and then negated the sign, of it. You see, so that's somewhat sort of opposite to what happens with the mutation, right? If we mutated a population at the vertex 4, then what would happen is that the value at 4 would change sign, yes, but it's the directly neighboring vertices that would add a copy of the, and then negated the sign of it. You see, so that's somewhat sort of opposite to what happens with the mutation, right? If we mutated a population at the vertex 4, then what would happen is that the value at 4 would change sign, yes, but it's the directly neighboring vertices that would add a copy of their population to 4. What's happening here now on this weight level is sort of, in some kind of sense, the opposite. The weight value at the vertex in question does change sign, just like in the other case. But before that happens, that is copied to each of the directly adjacent neighbors. Okay, so this should sound very much like the Pentagon game, right? Does it sound very much like it? Right? In Pentagon game, what happened? What happened to this value y? Well, we add it to its neighbors, x and z, and then we reverse the sign of y. That's exactly what we're finding here. So what's happening with the Pentagon game is the same kind of thing that's happening with these weights. All right, so here's a great little exercise for you to see if you understand this and if you can make it work for something else. So suppose we want to increase the population here further, right? Then this weight vector will tell us the most efficient way of doing that is to mutate at the vertex 3, because that's going to result in the biggest increase in the population. So you might try that. You could mutate at vertex 3 here and see what happens to the corresponding weight. See if the transition from this weight to the weight of the new population is given by the same kind of rule. Okay, so this is opening up a whole new sort of aspect to this dynamics on the graphs story, because now we have another kind of dynamic, which actually has quite different properties, as we'll see. Well, there's many similar properties, but it also has quite a different nature somehow. It really has maybe almost like more of a dynamic aspect.